I'm very pleased to introduce John DeNero. So John is a graduate student extraordinaire at UC Berkeley. He's getting quite late into his PhD and will be looking for a job in a year and a half or so. So if you're looking to hire someone, definitely keep him in mind. So John is going to be talking about estimation problems in machine translation and looking at the word alignments and other aspects of the problem that Adam teed up. So he gives great scientific talks, so I'm hoping that his lecture will be equally good.
Yes, thanks, Chris. Okay, so here we go into some of the details of what makes these machine translation pipelines actually work, actually generate good translations at the end of the day. But I guess before I start, can I see how many people are part of the MT workshop that's going on this summer? Okay. And how many people are part of other kinds of workshops? Basically everyone else. Okay, I just wanted to get a sense of what the mix is. As I'm talking, since we're actually going into the details of stuff and looking at particular equations and things like that, feel free to stop and ask questions. I think you'll probably get more out of it that way. So far, what you've seen is a bunch of different, what we call models, but really formalisms of how to translate. Should I grab words at a time? Should I grab phrases at a time? Should I grab grammatical chunks at a time? And we're going to search over this big space of all the different ways that I could translate a sentence, and what we're trying to do is find the highest scoring sentence. So now we're in the business of assigning features to the different pieces of the translations that we're building up, and scoring these translations so that when we do this search, we're actually searching for one that's better than the rest. So the choosing features and choosing weights for those features and choosing scores are all types of estimation problems. And machine translation is interesting because in many tasks there's just one model, one estimation problem that you want to solve. But machine translation is built in a big pipeline that has lots of different estimation problems in it. Okay, so let's think about what exactly it is that we're going to score. And here's one of the things. This is the hierarchical phrase-based model that Adam told you about. So my Spanish is slightly better than my Chinese, so I'll do some Spanish, but neither of them are particularly good. Here's a sentence we want to translate. Lo haré de muy buen grado. And the two grammar rules we're going to use to translate it are down here at the bottom of the screen. Can people see the bottom of the screen? Yeah, probably. So one of them just grabs a phrase and says, I can translate this as gladly. The other one says, once I've translated anything that is surrounded by lo haré on one side and a period on the other side, then I can consume the rest of the sentence. So I've used these two grammatical rules which cover all the lexical items in my input sentence, and I've generated this output thing. And it's color-coded to say that this object, which we'll call a synchronous derivation, is the kind of thing that we can assign a score to. And the way we assign a score, as Adam indicated, is that we pick out different pieces of the synchronous derivation and we score those. So the language model scores the string of words in the output by just saying, what's the probability that I starts the sentence? What's the probability that will follows I? What's the probability that do follows I will? In a kind of linear chain sense. And the translation model are weights on these rules themselves. And they say things like, for all of the different ways that I could translate de muy buen grado, what's the probability that I'll use gladly instead of happily, or instead of the dog, or all the different ways that I could imagine translating this phrase, some of which are good, some of which are bad, and we want to come up with the probability distribution over all the different ways of translating it. Likewise, for rules like this, for anything that says lo haré and then some gap, x, period, what are all the different ways of translating that into English? So the score that we generate says it's a product over words in the output. I've written product from 1 to I, where big I is the size of the English sentence, of each English word conditioned on whatever previous words came along before it. And then we have things like, what's the probability of the English side of each rule given the foreign side of each rule? And it's also nice if, when we translate something, were we to translate it back, we'd get something close to where we started. So in fact, we include in our models things like, what's the probability that this foreign sentence, and sorry about the English foreign thing, it's a historical issue in machine translation where everything was originally translating French into English. So we'll just say we're translating into English from now on, but if you'd rather think of it as source and target, yes, it is the case that more people want to translate out of English these days than into English. But just by convention, we're going to translate into English. Okay, so we also want to know for each rule that we're going to use, what's the probability that we'll get this foreign side of the rule given the English side of the rule. So now we just want to figure out what are all these probabilities. And the language model, which is the top, you guys already learned about. And I'm not going to talk about it. I'm going to do exactly what the machine translation community did, which is ask the speech recognition people, hey, can we borrow your model? And they said, sure, have fun. So we learned something about what English looks like from them. And we'll focus on coming up with these conditional probabilities of one side of a rule given the other side of the rule. We also, at the end, need to estimate these lambdas. And these lambdas say, how much do I care about getting the language model right, which is some notion of fluency, versus getting the translation models right, which is some notion of adequacy. How close is this to the original sentence? And we want to fiddle with these, but we won't fiddle with them for a while. We'll just focus on these numbers first. So we've seen a bunch of different models of how to translate. Word-based, phrase-based. And in 1993, it all began with words. So we have yo lo haré mañana, I will do it tomorrow. The parameters that showed up in this model were word translation parameters. How likely is it that the translation of mañana is tomorrow versus morning? And then life went on. We moved to phrases somewhere around 1999. People will quibble with my dates, I'm sure, but we'll get parameters that look like this. They'll say, for this whole phrase, lo haré, how should I translate it? And in the new millennium, we got even more sophisticated. So we had this pair of sentences. We can do things like parse the side that we're trying to translate. And we can extract big pieces with gaps in them and get all kinds of interesting rules that say something like, I can build a whole verb phrase, but it's missing the noun phrase. And if I see this grammatical structure on the side that I'm trying to translate, then I should translate it into this grammatical structure with some probability. Okay, so we can imagine assigning probabilities to all these things. And you might think, well, we have all these different structures. The world's changing out from under us every 4 years or every 5 years. We're going to a new kind of model. Do we have to redo all our estimation? And the answer is no. Most of the estimation that we do today is still about aligning words. So this is one of the dark secrets of MT, is we talk about moving to the syntactic layer or adding more information in, but a lot of the underlying machine learning that happens in the machine translation problem is about first aligning words with some probabilistic model like the ones we'll talk about today. Then once we've aligned the words, so this is like an example sentence that we've already seen. And once we've aligned the words, then we can infer the presence of larger structures. So just because all the words in lo haré are aligned to all the words in will do it, and nothing kind of violates the boundary of this circle that I've drawn, I can say, oh, here's a larger structure I'd like to translate with. And it turns out that most of the estimation game is making sure that you have the right bits to tile back together, that you've chosen the right phrase pairs or the right grammatical structures to include in your model and include in your search. And word alignments can get you pretty far. In fact, they're still basically state of the art. Okay, any questions so far? Let's align some words. So unsupervised word alignment is the problem of, given a large bitext, so the European Parliament has translated all these sentences for us, or the UN or whatnot. We know that translation's on a sentence level. We know something about what word alignments look like. And that's going to be very important. That the structure of the object we're trying to find is going to influence what models we choose. And we're going to build something like this. So if we have this set of words, this sentences in French and this sentence in English, we want to figure out where the alignment points are automatically. The unsupervised part, of course, means that we're not going to have anybody hand align any data for us. We'll have a little bit just to test and see how we're doing. But for the most part, this is a problem where all we can do is look at the sentences, know the structures we want to find, and find them automatically without having anyone kind of annotate our data for us, which is a great help because that's how we can translate from many languages to many languages without a whole lot of help from annotators. And in fact, this is a problem where unsupervised methods basically work as adequately or almost as well as supervised methods. In fact, if someone annotates a bunch of data for you, you still can't do better aligning than an unsupervised model unless you train the unsupervised model too and kind of inject that information into the supervised system as a feature. So what that means is that there's this problem of just figuring out what aligns to what is something that you can do without alignments and quite robustly. Yeah?
So why is that? Is it, I'll give you a couple options, you can choose to come with your own.
Okay.
Is it that the amount of data required to learn this problem is so large that we don't have supervised data at that scale? And therefore, it's always better to just use more unsupervised data?
That might be the case, but what are my other options? I have something to say about that.
Okay. People are so bad at this problem that the labels we learn from supervision are worthless anyway?
No, it's not that.
Okay. It could be that it's just a really easy problem.
Yeah, so part of it is that it's a really easy problem. The tricky part is getting the rare words all lined up. And rare words don't show up in a small corpus. And so if you have some small corpus, then, and that's the only thing that we ever get hand-aligned is some small number of sentences. So these statistics about where rare words show up in or co-occur with other rare words in the other language is really important, and that's the kind of thing that you get out of models.
So if I aligned a corpus, so let's say the standard supervised corpus has how many sentences?
400.
Okay.
So occasionally we can get something like 5,000, I think, but usually people just run it on some small number, like 400.
So let's say it's 400. Let's say every sentence is 20 words, so we have 8,000 alignments. Right? So let's say I give you 8,000 alignments on a corpus, but I guarantee every alignment is a rare word. And I just don't align anything that's not rare. Would that, do you think, do better?
I'm not sure I follow your setup, but I'm quite sure you need the large corpus of unsupervised data in order to get this problem to work. You need lots and lots of lexical level statistics. And those come from large amounts of corpora. But once you have a ton, a million sentence pairs, that's about all the information you need to figure out how the words line up. So that's why the unsupervised methods work. So it is kind of an easy problem in that sense. So let's look at some word alignments. Here's an infamous sentence, I guess. This is the first line of the Europarl corpus, which is a transcription of the European parliamentary proceedings. If you work in MT, you will see this sentence again. So let's just look at it now. I declare resumed the session of the European Parliament adjourned on Friday, 17th December 1999. Okay, so let's see how we would align this up. Here's how I would line it up. I would say that declaro means declare, reanudado, reanudado, excuse me. It doesn't quite mean resumed, but it's close enough in the structure of this sentence. El means the. So we're going kind of word to word, word to word, word to word. Now, there are more words to express this concept of session in the Spanish than there are in the English. In the Spanish, there's a contraction of de and el to del. In the English, there's 2 words. So now we have some one-to-many and some many-to-one structures. We have some crossing structures. So we talked a lot about reordering before. Here's some reordering that goes on. And down on the bottom, you can align a lot of things up one-to-one, but occasionally it just doesn't feel right. So we could align December to diciembre, but aligning 1999 to pasado just seems wrong. You might feel like, well, I should align this whole phrase to this whole phrase because they're meaning the same thing. So some insights. Properties of word alignments. Most of them are one-to-one or many-to-one. You can capture most of the phenomena you want just by kind of drawing one-to-one lines or maybe 2-to-1 or 3-to-1. And usually the 3-to-1 groups are for contiguous phrases, though not always. So all these generalities that I'm going to claim, from a statistical modeling perspective, they're certainly going to be violated. But sometimes having a constraint that usually holds helps you learn more than it hurts you because you're eliminating stuff that you kind of is outside of your model class. Yeah?
Yes. What about these kind of like non-denominal alignments, like on and L and this stuff? How do you deal with those?
So we call them null aligned. They just appear. So in these alignment models, we'll say, oh, words are allowed to just spontaneously appear in one sentence or another. And you are going to learn something like which words like to just appear. So the word I likes to appear in English when you're aligning to Spanish because Spanish likes to drop the subject. Yeah, so the model's going to have to incorporate that. So here's another thing, is there are some words that are null aligned. That's worth keeping in mind. Okay? So we're going to use this one-to-one and many-to-one constraint, even though sometimes it doesn't quite feel right, because it's going to help us get into the right ballpark of what the solution should look like. So let's try something simple. Heuristic estimation. This says, how do I guess, given a large corpus, what words are aligned to what? Well, I can observe that if two words show up, an English word and a Spanish word, show up in the same sentence pair many, many times in a row, then probably they should be aligned. So I can go through and I can count the number of times that E and F appear together in a sentence pair. And then I can say something interesting about what words align to what. Now the reason this is going to break is that what's the most, let's go back to this example. Let's say I want to figure out where interrumpido aligns to. What's it going to co-occur with most? The. Or maybe comma, or maybe period. So that statistic isn't quite right, but you can get some mileage just by looking at something very simple. So this is where I say this is not that hard of a problem. You can get reasonable word alignments, although they're not good enough to be used in practice, just by doing things like count the number of times I saw a word, count the number of times I saw, oh, this should be word E, I'm sorry. And then come up with a coefficient that says, if I saw this thing together many times, but the denominator says these words are reasonably rare in practice, then I'll get a high dice coefficient. So for interrumpido and the, this is going to show up everywhere in my corpus, so I'm going to get some big denominator. This number is not going to be that big. But for interrumpido and interrupted, or some reasonable translation of it, we'll get some high joint frequency count and some reasonably low counts. So this is going to give us some number between 0 and 1 that will be high for words that showed up or co-occurred a lot. So simple. And you can run this, and then you can say things like, I want to align the word, each word in the foreign, to the English word that gives me the highest dice coefficient. And something reasonable will happen. You'll already be getting some things right, but not enough right. And the thing we're not quite getting enough right is the reason we had to divide, the reason we had the control for the word frequencies is because we want to enforce some sort of competition between explanations. And this just says, if the is there, and it co-occurs with interrumpido a lot, and we still shouldn't align it because there's a much better explanation of why the is there. You know, L is there. Right? There's a better translation for it. So you can heuristically enforce some competition across words to say, I only want one good explanation of why this word is there, interrumpido. Well, because there's some reasonable translation of it. And there's only one good reason why the period is there. It's because there's a period in the other side. And there's some amount of heuristic literature on how to kind of come up with these estimates, but then there's kind of a better way. And that's a probabilistic model. So probabilistic models, because they have a hidden variable which aligns the words, will naturally impose competition. So here's how it works. We say, well, here's how, this is IBM Model 1. So how many people have seen IBM Model 1 before? Almost everybody. That's okay. We'll walk through it. I think it's interesting. I have some tweaks on it at the end to keep people interested who have seen it before. So what we're doing in IBM Model 1 is we're saying the English is there. It's observed. And what we're going to generate is the foreign sentence. And the way we're going to generate it is word by word. And that's going to give us word alignment. So each word is in fact going to be not only generated, but kind of word by word, but it's going to be generated independently. And the big trick with an IBM model is to say that there's some hidden alignment vector that encodes for each position. Here's what it might encode. It might say the alignment vector, so it has 6 elements, 1 for each position in the foreign, and its value is what position in the English it aligns to. So this structure that I've drawn can be encoded as saying A1 is 2, blah, 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 blah. A6 is 5. And this alignment structure is hidden. That's the thing we want to discover with our probabilistic model. OK, so we're generating each word. We're generating each word conditioned on a particular word in the English. Here's how we can write down the probability of the whole foreign sentence and a particular alignment vector that goes along with it. It says it's a product over all the positions in the foreign. What's the probability that I made that alignment? What's the probability that I aligned 5 to 6? Given here's the length of the English sentence, here's the length of the foreign sentence. Those might be important when we're deciding this alignment. But then more importantly, we have, now that we've chosen this alignment, we can say what's the probability that this foreign word was generated from this English word. And now we have multinomial distributions over all words in the language, which say for any English word, like session, what's the probability that any foreign word is generated from it? Questions about that? It's got to be one. Even a correction or a... OK. No. All right.
Get over here.
Yeah. Shoot.
How do you get the order right in periodic decisions if you're generating all of your words independently?
So that lives in this probability. So what's the probability that I bothered to align A6 to 5?
But, so all 3 of those words are going to align to session, right?
That's right.
So what prevents them from showing up as the periodo sesiones or something, out of order?
That's a great question. So in fact, if I made a broken sentence that said de sesiones periodo, that would get the same likelihood under this model. So this model is not that useful for translation, actually. But it's good for alignment. So why do we don't have to worry about that case so much, because everything that comes in is reasonably formed English and foreign. So yeah, you're right. We're only modeling kind of part of the process. We're making lots of simplifying assumptions here, just to kind of keep things very simple so that we can use a large corpus and let those corpus statistics filter through and give us a reasonable answer. Other questions? Yeah.
So the goal here is to produce the best alignment, right? And you observe foreign and English. So why don't you write a probability that says, find me the best alignment given foreign and English?
So the question is how you train it, what objective you want. And so this is convenient because we're generating both the foreign and the alignment. We can maximize the likelihood of the foreign sentences that we observe. If all we have is the alignment, and we don't have any examples of alignments, it's hard to say how we'd maximize the probability of the alignment, I guess. So the reason this is going to work is we're going to say, give me parameters for this, such that I'm not so surprised to see this foreign sentence aligned to that English sentence. So if I had the right parameters, then I'd say, oh, declaro el periodo de sesiones. Of course that's what I should say. Because session translates into these words, and L is a good translation of the, etc. So we want all of these probabilities to be high. Now remember, we haven't figured out what these are yet. We're going to need an optimization procedure to figure those out.
So actually, I think you're right. I mean, from a classic EM standpoint, the actual data that's hidden during alignment is only the alignment grid.
That's right.
Everything else is observable. So from a classic EM standpoint, you have some hidden data, which is just the alignment grid. You've got observables, which are the X and Y. And so if you had a way, if you could come up with a procedure for simply estimating that hidden data, right, based on those 2 observables, right, that would be a good thing. The reason we don't do it typically is because it's just too hard. don't know how to search that space efficiently. And so instead we have this sort of hierarchy of models where we start with a relatively easy one like model 1, which we can search very efficiently. We transfer some parameters to the next model and so forth. But I think you're right. That what you really want is to treat that alignment grid as your hidden variable.
The alignment grid is certainly the hidden variable. Yeah, so I completely agree there. I guess if all we wanted to do was build a model of alignment given these sentences, we'd have to say, what alignment do we want?
You want the alignment that maximizes, right? Under some model, you need some model.
Uh-huh.
So presumably this model then would have elements in it which produce words in both directions.
Right.
So each element produces words in 2 directions, and then some model of distortion built into it. Right, so what does that model look like, I think is exactly the question.
Yeah, that's a good question. And so what I'm saying is from an unsupervised perspective, if no one tells us what these alignments look like, then all we can optimize for is explaining why we saw the data that we saw. So I want an alignment that helps me make sense of the fact that this is the foreign sentence that came along with this English sentence. So that's kind of why it works. I guess if you have a model that just looks like, what's my alignment given my English and my foreign sentence, then you can do things like, if somebody tells me what alignment I want, I can find a model that maximizes the conditional likelihood of that alignment. But that's more of a discriminative technique. You need someone to annotate your data. If all you have is unlabeled data, and this is truly a hidden variable that we don't know anything about, then we're going to need to, for instance, explain the likelihood of the data that we're generating.
But you got to invert that. You got to use Bayes' rule. You're going to invert it and say, what is the probability of the alignment, and then probability of E of F given the alignment, which will then decompose into smaller factors, right, which are small groups of English and French words popping out of that alignment.
Yes.
So
as long as we have a term that says what's the probability of E and F, then it will work.
That's right. So,
and we're doing something similar here, except we're only doing F instead of E and F. So it's a good point, and you can definitely write down models that look exactly like that. Okay, so I think we basically all agree. Let's move on. Okay, so there is some issue with reordering here, which says I've said that what's the probability that I'm aligning this word, the 6th word in the foreign, to this 5th word in the English, and all I'm going to do is condition on the length of the 2 sentences. Well, that seems like a bizarre thing to do. Model 1 does something even more bizarre. It says, I'm going to have a uniform distribution over where I align. So it says there's a probability of 1 over the length of the English sentence that I align to a particular place in the English sentence. And this is the most broken assumption in Model 1, and we're going to fix it later on in the talk. And this I plus 1, well, actually you can align to this hidden null word over here, which you guys mentioned before, to say, actually, I want to be able to generate words in the foreign that don't align to anything. And likewise, you have a distribution over what words like to pop up conditioned on nothing at all. OK? So in the lab today, how many people are coming to the lab? All right. In the lab, we will build Model 1. And then we'll make it better. So what we need to learn, and here's how we do it. So this is an important slide for people who are coming to the lab. The free parameters of the model are these probability of the foreign word conditioned on the English word. And the goal is to maximize our data likelihood. It's to maximize what's the probability that this foreign sentence is generated from this English sentence. Because I see it there, I need to be able to explain why it's there. So here's how it decomposes. In the expectation step, we compute the expected alignments, or the alignment posteriors. And here's a term like what you guys were talking about. It says, what's the probability that in a particular sentence, so I've now bolded E and F to say these are whole sentences E and whole sentences F. And these are just word-to-word probabilities. And this says, what's the probability that this alignment link exists? What's the probability that position J is aligned to position I? Well, there's this likelihood term which says, I picked this alignment, I, uniformly at random, and then I generated this foreign word. And I normalize this by saying, what are all the different words I could have aligned to? Those are I primes. And for each of these, I could have picked I prime with just that same probability. So the prior on the alignment that I choose is just some 1 over the length of the sentence. And then there's the chance that I could have generated this foreign word from some other English word as opposed to the one I picked. So this is going to give you a probability distribution, meaning if I look at all of these, they'll sum to 1 over all the different positions in the alignment. And it's going to be the posterior under the model of where this thing aligns. And this is exactly what we want. We want to figure out where this thing aligns. And it's all driven by these lexical parameters. So we have these free parameters in the model which we just initialize to uniform. We can initialize them however we want. And then we compute under our current guess of this conditional probability what the alignment posteriors are. They'll start out wrong, but they'll get better and better. And then the M step of EM is to say that our new guess as to the probability of the foreign word conditioned on the English word is the sum of the posteriors, these guys, for all the times that we saw this foreign word and this English word together. And I promise I'll write this up somewhere during the lab. And then what are we going to divide by? So this is how many times I saw foreign and English together. Well, we want a conditional probability. So we want to find all the times that we aligned to the English word at all. And that goes in the denominator. So this looks over all the different foreign words that we could have aligned to and sums all those up. So we compute these for each sentence. And then we compute this for each word pair. And we repeat, say 5 to 10 times. And what we're doing through this process, though I haven't given you the full derivation, is to say, find me these statistics, probability of F given E, that explain the foreign sentences of my corpus as well as possible under this model. OK, questions? Yeah?
Why not repeat until convergence?
Repeat until convergence is a good idea, too. It tends to be that you can repeat this particular model until convergence, and it will work fine. Sometimes you get, with more complicated models, sometimes you get some nice regularization effects by stopping early. But that's kind of the black magic of machine learning that we won't worry about. So mostly for time constraints, you don't run it forever. OK? OK. So we're going to run EM, which looks like this. And now we've explained why the foreign sentence is there, given the English sentence. Now we have to do something with these parameters that we've come up with. And there's 2 obvious things you can do with them. One of them is called the Viterbi alignment. So now I have this sentence, this training sentence pair. And I've computed the posterior probability of every possible alignment link that I could draw. And now I might want to compute for each foreign word, what's the best English word I could align it to? It's called the Viterbi alignment. So you just compute all of these, and then you pick the best one for each foreign word. So for each J, pick the highest I. Posterior decoding is something slightly different. So this gives kind of competition among explanations, just like the model does, and it's a good idea. Posterior decoding is a little different. It says, for any alignment that seems plausible, meaning its probability is above some threshold. And you could make this threshold pretty low, like 0.1. Include that in my final alignment. And this will give us control over how many alignment links to posit. So if I want kind of everything that I think could possibly be the case, then I could use a low threshold. If I only want the alignments that I'm almost positive are there, then I can use a threshold of like 0.9. This gives us some leverage of using the predictions under the model to decide exactly what I want to line up. OK? Onward. So how do I pick this threshold? Is a good question. And that depends on what I want. So what I want, here's where we have to get a human in the loop. One way to evaluate alignments is to kind of translate with them. But then you need a language model, you need rules, you need all kinds of complicated infrastructure. Another way to inspect them and see if you're on the right track is to get a human to align some things. And then check how well your alignments match up to the alignments that the human said should be there. A common, though occasionally maligned, evaluation metric is to have a human to go through and mark where the word alignment should be. And occasionally they don't know, so they put things like possible. And you can either have the human say, oh, this is possible. That tends to be a bad idea because then they put possibles all over the place because they don't want to be wrong. Or you can get a bunch of humans to align the same thing, and where they don't agree, you can call those possible. But the point is, now we have a bunch of alignment links that we were supposed to predict. And then we predict some of them by saying, whenever this alignment link is above the threshold of 0.5, then I'm going to say that's the period is aligned to the period. And I compute the following thing. This is a lot like F1 for precision and recall, but you get to cheat a little bit. So for precision, which says how many of my alignments were correct, they're correct as long as they're either sure or possible. And for recall, which is how many of the alignments that I should have predicted did I actually predict, I only have to predict the sure ones. So this notation encapsulates that in some set notation. But the point is that we're just computing the harmonic mean of this precision and this recall. This will give us some number between 0 and 1. And since there's an error rate, 0 is good, 1 is bad. That's why we have 1 minus the whole thing. OK, questions? So now we have some metric that tells us if we have an alignment and we have some human alignment, how well are we doing? And for the rest of this talk, I'm going to give you some numbers on a common data set that tell you 4 different models how well they do. So how well would this do? Well, we'd have 3 right. That's the kind of numeral, well, whatever. You can do the math. 3 plus 3 is 6, and 3 plus 4 is 7 possible things that I should have accepted. And so I have an error rate of 1/7, which is pretty good. Yeah?
How do you, when you're evaluating alignment quality, how do you deal with the fact that different annotators might have different sort of levels of granularity that they mark up the data in?
Mm-hmm.
Sometimes you might get something marked as kind of a totally filled in square, and sometimes it might be like, you know, just the points along the back.
Yeah, good question.
Yeah.
So half the battle is giving annotators specific directions and hoping that they agree. Because some of the early annotated data sets that are still in use today have wild fluctuations and do exactly the wrong thing. And so it turns out usually when we're going to use these alignments for later on in the process, like I said, you actually kind of want things aligned as a word level as opposed to having some big region and saying anything in here is OK. Because usually anything in there is not OK. And you'll get worse alignments if you optimize for an objective like that.
And the related question is that the alignment models can sometimes hypothesize links that are sort of partially fill in a square but don't totally fill it in. I think sometimes people use the sort of the transitive closure to sort of totally fill in those squares. Is that considered the best practice for?
Yeah, so this is, so let me draw something for you guys. Let's say I had the dog, El Perro, and I filled in that box, and that box, and that box. The transitive closure just says, why didn't I fill in that box too? Because clearly I've tied all these things together. And this is important because later on, we're going to try to infer larger structures, like the dog as a unit goes to El Perro. And whether we've drawn these 3 points or we've drawn all 4, we're going to get the same answer. So in fact, the way we use alignments oftentimes is invariant to whether or not we fill in certain points in the context of other points. Yeah, so sometimes, so the right thing to do is to complete the transitive closure and then evaluate that. Time flies. OK, so what's wrong with IBM Model 1? Well, one thing is that it aligns too many things to rare words. This is just an empirical fact. If you run the model, then it will do things like this. It will take this word loading, which has a perfectly good translation, and we found it. But it's also aligned the quotes to this word too. Now, why on earth we would align the quotes to this word beats me, but all we're doing is optimizing some objective. And the point is that this word is so rare that it's kind of indistinguishable from anything else. So we can get a probability distribution that says I crank out each of these things with a probability of 1/3, which is pretty high, and therefore I get a pretty high likelihood. The other problem is that we haven't handled distortion right at all. We've said there's a uniform probability of aligning to anything in the sentence, and that's just wrong. So we're going to try to fix both of these things. So let's see if we can clean this up. Oh, I did it. How did I do it? Well, we can intersect IBM Model 1 in both directions. So everything I've been talking about so far, let me just talk for a minute. Everything I've been talking about so far is generating the foreign sentence from the English sentence, and therefore aligning each foreign word to some English word. And I could run the whole model in reverse. I could generate the English from the foreign, align the English to the foreign words. And if I do that in both directions and I intersect the output, I'm going to result in a 1-to-1 alignment if I'm doing Viterbi alignments instead of many-to-one. Because they're many-to-one in two different directions. And they're going to get rid of things like aligning a whole bunch of stuff to the same place. So let me start with some numbers. These are alignment error rates. If you train the model in one direction, if you train the model in the other direction, and then if you intersect them. So look at what's going on here. We had precision and recall numbers that were 80 and 60 about. And now we've jumped up to a really high precision of 96, which is pretty surprising. I mean, these are really simple models. And all of a sudden, 96% of the alignments that I'm offering out there are correct. This is actually over-exaggerated. There's something a little bit funny with this data set. This is the Hansard's corpus, for those of you who care. But the point is that you can do pretty well with this intersected Model 1, but you lose a lot of recall. So we're not really getting a full alignment. We're missing some stuff. So now our AER is 34.8. So here's a trick that works really well and is almost as simple as running Model 1. That's not quite as common because it's more recently discovered, but I like it a lot. So we can intersect the model after we've done all of our alignment, or we can intersect it as we're training. And what intersecting it as we're training means is remember we were computing these posteriors of what's the probability that an alignment is there given these two words. Well, these two expressions are identical, but they're under different models in different directions. So you can say, what's the posterior of this alignment being there? Well, it's only there if this model thinks it's there and this model thinks it's there. We can multiply these things together. Now, if you do this, all of a sudden you have almost as high precision as you did before, and your recall goes way up. And now we have a number that's getting close to respectable. An error rate of 20. So that's like a little bit of magic in the middle of the training procedure. When we're running the E step, we multiply the posterior predictions of two different models together. Any questions about that? Yeah?
So there's some debate when you do this about exactly what function you use. So one is you multiply, which means that they both have to agree.
Mm-hmm.
You will have to at least give some thought to what you're going to do about the null word if you're going to multiply.
Certainly. And those are details that I'm not going to dig too into, but you're right that they're sometimes complicated.
You could add them, which is something that folks have done under certain conditions that gives you different results that aren't necessarily yours.
Mm-hmm.
What's your thinking here?
So the reason why this seemed to work was that the system made orthogonal errors that really did look like they're aligning a bunch of stuff to one word.
The recommendation is
Yeah, and so multiply is like in a soft intersection.
yes.
So we just wanted that intersection effect, and this is how you could get it. OK, so really simple model, subtle tweak on EM. We're almost in business. What was the other thing that we were doing wrong? It was that we're modeling distortion in a completely bizarre way. If I align the first word to the first word, there's nothing stopping me from aligning the second word to the 18th word in the sentence. And that sounds like trouble. So here's an improvement. IBM Model 2. Not quite twice as good as Model 1. Which just says words at the beginning of a sentence should align, words at the end of a sentence should align. Do something about the position. So we had this term in Model 1 which says, I want to know something about the alignment probability, just given the lengths of the sentence, without really looking at what words are there. So some prior over alignments. And model 2 can be parameterized in various ways, but here's a simple one. It says it's proportional to the difference between the alignment that I choose and the alignment that I should have chosen if I just did something monotonic. So you want the first thing to line up with the first thing and the 8th thing to line up with the 8th thing. This I over J adjustment just says if one sentence is twice as long as the other one, I want to scale this monotonic business. Okay? So really simple stuff. I have some term in here that now says I like alignments that go down the diagonal better than the ones that don't. So this was kind of a good idea, but it actually wasn't quite right. Because here's what it didn't get. You do want monotonic alignments, but you want locally monotonic alignments. But sometimes this whole chunk, like Tuesday, November 4th, moves from the beginning of the sentence to the end of the sentence. And we don't really want to pay for that movement 3 times over just because there are 3 words. Instead, we want to say, okay, some phrase has moved from the front to the back, and I want my alignment model to capture this. Now, what does it mean for an alignment model to capture this? Well, it wants to say something like, if I just aligned to 8, the next thing I should do is align to 9. And the next thing I should do is align to 10. So look back one step, see where you aligned, and then decide where to align the next word. So now there's actually some structure to our alignment vector. We want it to be locally coherent. Does that intuition make sense? Okay, here's how we enforce it. We're almost to state-of-the-art performance. So here's a sentence that we're trying to align to the English. Gracias, lo haré de muy buen grado. One way of viewing this is as a graphical model that's entirely disconnected, where we're deciding where to align. So here's the hidden alignment vector. This is going to take numbers. The numbers correspond to positions in the English. And in model 1 and 2, all we had as our model parameters were what's the probability of the foreign word given the English word, and then some transition, some probability, well, it's not really a transition probability, this is a misnomer, some probability that the alignment is what it is. So 1 goes to 1 we like, 3 goes to 3 we like, etc. Some of these we really don't like. Like the 3rd word going to the 7th word, etc. The improvement over IBM models 1 and 2, which is my personal favorite, and gives us state-of-the-art performance with some other tweaks, is the HMM model, which you guys saw HMMs a couple days ago and probably many, many times in your life. This is to say, all I want to do is condition on where I align to based on where I just aligned the last word to. So this is parameterized. We still have the probability of a foreign word given an English word. But now we have things like, I just aligned to position 1. What's the probability that I now align to position 3? So these are simple statistics too. They just say, where was I? Where am I going? And what's the probability of that? This gives this connected structure in the graphical model, which says these hidden alignments that we don't know where they are should be locally coherent in some way. Questions about that? Or this picture?
I've got a question.
Yeah.
So what about places where you have things that should be discontinuous? I mean, this obviously would help with locally coherent places, but does it bias you towards local alignments?
It does bias you toward local alignments, often too severely. So there's an issue here where this is the lesser of two evils, I think, relative to Model 1. I mean, no, it doesn't. I mean, this is not a hard constraint, of course. You know, these are just parameters, and you're allowed to violate them. So most of this model's predictions are still going to be driven by the lexical statistics, because those are, you know, big numbers. You know, sometimes this will be gracias given thank is going to be like probability 1/2 or something high. Whereas a transition probability is going to be something flatter. You know, it's going to say, yes, I prefer to go to the next word, but I wouldn't mind staying where I am, and jumping around in the sentence is not so bad. Reasonably flat distribution. Yeah, so sometimes it works out anyway. But you're right that this is not capturing the whole story by any means. It just happens to be this is a very efficient model because we can run EM on it. And we can run EM on it, 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 and we can run With the forward-backward algorithm, it's not that much more complicated than running IBM Model 1. So let's look at this HMM model in a little more detail. Model 2 preferred global monotonicity. Now we want something local instead, which says we're allowed to jump around, but once we've moved a phrase, we want to be able to bang out that whole phrase without incurring distortion costs for every word in it. So this was proposed in its particular form a little bit later than the original IBM model. We're only at 96, right? We're not quite into the modern era yet, but these models are still used quite regularly. So this conditional distribution of a foreign word given an English word is just some probability distribution over how I should translate the word national. Usually this guy, which is the distortion term, is just parameterized by the signed distance between where I ended up and where I started. So if I just align to position 2 and now I align to position 4, I just take 4 minus 2, and I have some probability associated with that. And I learn each of these parameters. So I learn it's much better to walk one step forward in my alignment than to jump 2 or to jump 3, but you get a reasonably flat distribution. Looks something like this. Okay? So this is still a really simple model. You're right, you can't really translate well with this, but you can certainly align well with it, because there's so much more observed when you align. Handling nulls requires some care in this model, but you can re-estimate it with closed form EM. You don't have to do any tricks or approximations, and it's fast. You can align millions of sentence pairs. Okay, so let's look at some examples of structures. I won't read out the words, mostly because my French pronunciation is quite bad, but it has the same problems. So if you have a rare word here, sometimes you're going to align a bunch of stuff to it because the model doesn't really know where to put it. And when you see this big box up in the upper left corner, that's because there was a non-literal translation going on of the first words in each sentence. And the model didn't know what to do with it, so it just aligned it to some where word in both sentences. So this is if I train the model in one direction, if I train the model in the other direction. And each one has this many-to-one constraint that all IBM models do. So what's the answer to this? How do we fix this problem? Intersect. Thank you for that. So we intersect. Let's see. The last time we intersected was with Model 1, and we had an AAR of 20. Just running the HMM in one direction or another does much better, because it has a more reasonable constraint on the alignments. So now we're in the 11-10 range. Intersecting these gets us down to 7. But if you do the joint training, now we're down to like a loss of 5. So that says as we're training the model, we want to make sure that the posteriors line up in the forward model and the backward model. And this is state of the art. So this is kind of how you do word alignment. And in fact, if you spent a couple days, you could implement this. There's nothing complicated going on. Or you can just download our aligner and use that if that makes you happy. As a point of reference, there's an older package that runs Model 4, which includes notions like the fertility of a word, how many things should align to it. And that makes EM a little bit trickier to run. It didn't happen to do as well on this data set. OK, so what you've seen at a high level will get you to pretty good word alignments. I mean, a 5% error rate is not so bad, right?
John?
Yeah.
Quick question. Before when you did the and, your AER went up, and now it went down.
Word or the phrase that you think it aligns to. So we're making this really hard independence assumption that says, all I'm going to look at is the word the when I translate it to L. And that's often a bad idea. And then some people are working on just spraying features everywhere. So every little bit of information that I can extract from this synchronous derivation, you know, how long is it? How many times does it use this particular grammatical symbol? How big was the reordering that I made when I kind of changed the order of two phrases? You know, you can come up with thousands of these and push all those into the log linear model and see what happens. And that's all I got. So if you have any other questions, then I guess we can open it up to more general questions. Yeah.
So as you point out, the alignment models are still very, very simple. And I know a lot of people spend a lot of time working on improving alignment. And there seems like a lot of information that you could add that would improve it that you're not currently using. But your error rates are fairly low. And there's so many other levers and switches making the system work. So this is now I ask your opinion. If you were going to go and spend time working on some part of this process, how much more is there to gain out of alignments versus other areas of the pipeline?
There's definitely room to gain from alignments. I don't know, people work on alignments both because you see obvious errors and you can fix them. And of course, why wouldn't you? Or you see obvious sources of information that you'd like to be in there, so why don't you just put it in? And it does make the alignments better. And you don't have to kind of build the whole system from scratch. And I'm glad people work on that. The only trick now is that the people that are having most success, I think, in the alignment problem these days are people that work on the general pipeline. So I think there's nice work coming out of ISI where they dug deep on Arabic-English alignments and added all kinds of linguistic information. And the alignments got better and the translations got better because they were really picking on errors that showed up much later in the pipeline. So that kind of work I think is nice. We've been doing some work on alignment, so I think we're not, the Berkeley group isn't finished with the problem, and I don't think anyone else should be either. That as soon as you make your alignments better, and then you put it into some publicly available pipeline, and the blue score goes down, don't quit. Call someone who wrote the pipeline and figure out why. Because there's usually things like how many alignments you posited, or particular alignment errors can cause big problems for phrase extraction, and you might need to get rid of those, and sometimes just throwing in a heuristic here and there can fix that kind of thing. So I think it's a fruitful area. I just think you have to, sometimes after you make your alignments better, you have to also fiddle with something a little bit later in the pipeline to take best advantage of it. Yeah?
So as you're trying to align, it seems like one of the worst problems that you run into is you have a supposedly parallel corpus, but it isn't.
Mm-hmm.
There's these noticeable chunks of it are not parallel. What's your opinion or suggestions in that direction, if any?
So those who take data set curation seriously do get better results than those who don't want to deal with it. So if you go through and you come up with reasons, so you have this parallel text, and it started out as parallel documents, if you're lucky, or you just scraped the web, and then you try to figure out what sentence lined up to what. And you're going to make errors. If you then go through and kind of purge those errors to the best of your ability, your performance can certainly go up. So one way is to treat that as a separate problem, to make sure your data is as clean as possible. Now these models are fairly robust to having a sentence and something that you call a translation, but it's really not. Because all you're doing is you say, I don't know where the alignments are. You add a little tiny fraction to the expectations of a bunch of different word pairs, but they don't really change the answer that much in the end. So I'd say, yeah, it's probably worthwhile to throw these things out, but if you don't throw them out, it still works. I don't know if that's satisfactory or what you were looking for.
Well, it's often the alignment. It's often your alignment itself that gives you some hint. Right?
Yeah. And one way of throwing things out is to ask what's the likelihood under the alignment model, and if it's really low, then you should throw it out. If it just has the words in it that you wouldn't expect, then that's actually the best indication I can come up with that this is a bad translation. I guess the other way to do it is you actually translate one of the sentences with your machine translation system and compute how close the result is to the thing that you think is the translation, and throw it out if it's not. And this is one of the more recent techniques for finding parallel corpora on the web, is to kind of translate the web and then find stuff that matches up with it. Question? Done? Question?
So we talked a lot about alignments today, and it's not clear to me, maybe you can tell me, what's the real definition of correct alignment? So for example, in your slides, 2 instances, I was, if I had to align it, I might have done it differently than what you had labeled as correct. One was when you had declara. I was inclined to put I declare,
Sure.
not just declare.
Uh-huh.
And the other one was similar, was array. I would have put the I with that also.
Uh-huh.
So does the field have a clear definition? Like you just gave us kind of an inductive definition. You had some examples and you said match up the words. But is there a really this thing, or does the field just kind of have this ambiguous notion?
I'm afraid to answer that question because I actually don't know the answer.
Sorry.
Does anyone else know the answer?
So the answer is not a very satisfying one, but we use the human alignments as the truth. And so that really depends on how good your annotation guidelines are. So for some sets, we just basically say, here's some sentences, align these words, without giving people any more specific instructions that would guide those ambiguous cases, like whether you align the pronouns with the Spanish verbs. The LDC has developed some more rigorous alignment guidelines for Chinese and Arabic, and they've invested in like huge amounts of word aligned data. So John was saying that normally we only have about 200 sentences worth for any given language pair, but for the Arabic and Chinese data that we're using in the Gale program, we have thousands of sentences worth of manually aligned data. And there they were a little bit better about developing guidelines.
And in fact, just to add something to that, in Gale, in the last year or so, there was tremendous debate about exactly what level of granularity for Chinese English alignment would align every word or not. And so the teams, the three main Gale teams, did not seem to agree.
Yeah, there's this problem where if you want to hand align something, then you have to decide where the word boundaries are first, and people don't even agree on that. It's a good point. Yeah?
So,
Oh, I'm sorry.
I'm from Carnegie Mellon, and we have this ruler, we're living on the ruler. So when we align some Urdu data, we first let the native speaker use her intuition about where the words align, and then we thought about how our rule learner worked, and we said, we're not going to get very good rules out of that, align it this way. Like it was, a question of whether an order auxiliary verb should align to a past tense mark or anything or something. Don't align, because our rule learner is not going to align anything. So, I mean, is it possible that it is really not defined? You just have to know what's going to work best.
Yeah, I think that's exactly right. I mean, alignment sort of means to an end. They're for a particular system, and yeah, you might want a different annotation standard for a different system. Now that's scary. Oftentimes you can have one kind of set of annotation standard and then fiddle with and then kind of edit them later or change your rule extraction algorithm or something like that to accommodate whatever there. But yeah, this is, we're using models that are too simple for the task and trying to get them to work anyway. So that's where I think that's the root cause of a lot of these issues.
Yeah, because that's actually part of the reason I thought of my question was because I used to work at ISI for a summer internship on the syntax system that you showed. And I think for their GHCAM rule extraction, it might be a little bit more easy for their system if you have the I aligned as well, because it could get that tree structure. It's more amenable. They might get it anyway, but
yeah, and they're doing. We've talked a lot about intersections to remove errors, but they're doing a lot of union alignments and then just kind of removing particular alignments along the way that are problematic for rule extraction. But yeah, a lot of times they want kind of more links is better. It turns out in some extraction algorithms, and things like that you'll pick up as you work on it if you want to stick around in MT. Yeah.
Oh, actually, my book was the same as Laura's.
Oh, okay.
Okay, I vote we thank the speaker and break for lunch.